Welcome back everyone. In this lecture we will see some applications of representation theory to group theory. So, I am going to actually reprove some of the basic statements that you must have seen in the first course in group theory using representation theory. So, let us actually see this very basic fact. So, any group of order prime square that must be abelian. So, let us actually prove that using representation theory. So, here is the fact. So, suppose G is a finite group of order p square, where p is a prime number, then G is abelian. So, we have seen already how to use conjugacy action to prove this result. So, now we will actually use representation theory to prove this result. So, here is the proof. So, what we are going to do actually we are going to use this important characterization of finite abelian groups in terms of representations. So, recall that G is finite abelian if and only if all its irreducible representations they are one dimensional. All its irreducible finite dimensional irreducible representations are one dimensional. So, let us use this characterization to prove this result. So, let us denote d1 etc. ds be the degrees of non-isomorphic irreducible representations of G. So, we write d1 etc. ds. So, this is all the degrees of irreducible representations of G. So, it is assumed that they are all non-isomorphic distinct representations. So, now what we know about these degrees. So, we know that the degree of an irreducible representation that is going to divide the order of the group. So, d I divides p square, which is the order of G. So, this is the dimension theorem that we have proved in the last class. So, now because d I actually divides p square, then that would imply that either d I is 1 p or p square, since p is prime. So, we can also assume that d1 is 1, which corresponds to one dimensional trivial representation. So, this corresponds to one dimensional trivial representation. So, it is always there. So, we can assume d1 is 1. So, now we want to prove that di equal to 1 for all I. So, now note that we also have this important relation between the order of G and di's. So, order of G is indeed given by d1 square plus etcetera plus ds square. So, now we have this d1 is 1. So, this is 1 plus d2 square plus etcetera plus ds square. So, this is already there. So, now from this it is immediate that since the order is just a sum of squares of di squares. So, that would immediately imply di cannot be p square for any I. So, and not only that, suppose di is p, then we immediately get, suppose di is p. So, then we immediately get that 1 plus p square should be equal to or less than or equal to p square, which is a contradiction. So, that implies actually d I equal to p cannot happen. So, that forces that d I is 1 for all I. So, that means all irreducible representations, so they are one dimensional for G. So, that would imply immediately that the group must be abelian. So, this is kind of implicitly uses the knowledge about conjugacy classes and so on. But anyway, this is very clean representation theoretic proof of the fact that we know from group theory. So, very similar to that, I also want to actually demonstrate another fact using representation theory. We all know that whenever we take the group which has order p q, let us assume p is less than q and q is not congruent to modulo p. So, any group of order p q satisfying these condition, that must be abelian. So, this is again known result. So, this would imply that G is abelian. So, let us actually try to prove this result using representation theory. So, for that purpose we need to actually understand all possible one dimensional representation of given G. So, let us actually make some observation about it. So, here is the lemma. So, this lemma again some facts about basic group theory, I am not going to prove it. So, I will leave it as exercise. So, if I start with the finite group and then we can define the commutator subgroup of G, which is usually denoted by the bracket GG. So, this is the commutator subgroup of G. So, by definition it is the subgroup generated by all the conjugates. So, this is the subgroup generated by all commutators A inverse, B inverse, AB, where AB comes from G. So, here are some facts about this commutator subgroup. So, commutator subgroup is always a normal subgroup of G. So, GG is always normal subgroups of G, normal subgroup of G, and when we take the quotient, that must be abelian. So, this is abelian, and not only that, suppose if we have another normal subgroup that actually gives us the quotient is abelian, then that normal subgroup must contain G. So, here is the third one. Suppose n is normal subgroup of G and G modulo n is abelian. So, then we must have that n contains the commutator. So, the n contains the commutator. So, these are some basic facts about the commutator subgroup. So, I am going to just leave it to you to check this. So, let us actually try to understand the relationship between the one dimensional representations and the irreducible representation of this quotient G modulo bracket GG. So, here is the proportion, which is not that difficult to actually prove. Maybe let me just state it here. So, if we are interested in understanding the number of one dimensional representations of G, so we can actually make some comments about it. One can prove that that will have exactly same cardinality as irreducible representations of G modulo bracket GG. So, basically there is a bijective correspondence between irreducible, of course, finite dimensional irreducible representations of G modulo bracket GG and the degree 1 representations of G, degree 1 representations of G. So, we want to understand all possible degree 1 representations. So, this bijection actually gives how to actually go to the abelianization of G and then get all possible degree 1 representations of G. So, in particularly this bijection tells us that the number of one dimensional irreducible representations, degree 1 representations of G, of course, non-isomorphic representations. So, that is going to be exactly equal to the cardinality of G modulo the bracket GG. So, we have already seen that for any abelian group. So, the finite dimensional irreducible representations of the abelian group is actually given by the dual group G hat, and which is exactly isomorphic to G. So, that is why the number of degree 1 representations of G is equal to number of finite dimensional irreducible representations of this G modulo bracket GG, which is exactly equal to the cardinality of G modulo bracket GG. So, in particularly we can conclude that this number of degree 1 representation of G that indeed divides the cardinality of G. So, the number of degree 1 representations of G that actually divides the cardinality of G. That is because it is just nothing but the cardinality of G divided by the cardinality of GG. So, this number indeed actually factor of cardinality of G, that is actually clear from the Lagrange's theorem. Okay, so, this proportion actually tells how to get all possible one dimensional representations of G. So, let us see how to prove this. So, this actually just uses some basic commutative diagrams. So, let us actually call this pi to be the natural quotient from G to G modulo GG. So, then if we actually take any one dimensional representation of this quotient or any representation of this quotient, then we can actually lift that representation to G via pi. So, let us take any representation here, call it rho. So, then we will be able to actually lift. So, this is called lift of rho. So, which is actually given by the composition. So, you just first apply pi and then rho. So, that is going to give you representation of G, which is going to act on V via this map rho composition pi. So, this is there for like any quotients. So, now we are going to just use this and then recover all possible one dimensional representation of G. So, what we do? So, we can actually start with some one dimensional representation. So, let us take xi to be one dimensional representation of G modulo bracket GG, because G modulo bracket GG is an abelian group. So, any irreducible representation must be one dimensional. So, we can just simply take this xi. So, then this is going to be a group homomorphism from G modulo bracket GG to C cross. So, this is what we get. So, now what we can do, we can actually use this pi. So, which is a map that is actually given here. So, this is the map pi, which is the natural quotient map from G to G modulo bracket GG. So, now what we can do, we can just pull back this xi using pi. So, then we get a map here. So, this is exactly xi composition pi. So, then this is the map that we are going to define from the set of irreducible representations of G modulo bracket GG to the degree 1 representation of G. So, let us consider this set finite dimensional irreducible representations of G modulo bracket GG. So, then from here we are defining map to degree 1 representations of G. So, what is the map? You take xi and then send it to xi composition pi. So, look at this diagram. So, this is the map. So, first you go by pi and then compose it with xi. So, this is giving one dimensional representation here in G. So, now what will be the inverse map? The inverse map is also very easy to write down. Suppose if we start with rho, which is a one dimensional representation of G, again it is a map from G to C cross. So, then you can see that you have G and then G modulo bracket GG. and then you have this quotient map pi, and then you have this representation rho which is given here. So, now since the image of this map rho, so that is going to be a subgroup of C cross, and C cross is abelian. So, this is going to be abelian subgroup. So, since this is an abelian subgroup, you can see that G modulo kernel is going to be isomorphic to rho of G. So, this is indeed an abelian. And now, since kernel rho is normal subgroup of G, whose quotient, the corresponding quotient is abelian. So, that means this kernel rho contains actually the commutator subgroup. So, that means, so this map rho factors through this quotient G modulo bracket Gg. So, then you will be able to define this rho tilde. So, which is actually, so this is the factor of rho. So, factor of rho, since this is possible because the kernel actually contains bracket Gg. So, that this diagram actually commutes. So, now, so what will be the inverse map? So, if I start with rho here, then we just map this rho to the composition of these two. So, you can easily see that rho must satisfy rho equal to rho tilde composition pi. So, we just map it to rho tilde here, and it is very easy to see. So, since rho tilde is a factor of rho, it must be actually a group homomorphism from G modulo bracket Gg to C cross. So, all the maps that are considered here, they are all group homomorphism. So, that actually tells you how to go from finite dimensional irreducible representation of this quotient G modulo bracket Gg to degree 1 representation of G. So, it is a very easy thing to check that this correspondence is actually one-to-one correspondence. So, we get a bijective map from one set to another set. So, now like I said, so the number of finite dimensional irreducible representations of G modulo bracket Gg. So, this is what we are interested in. This is exactly equal to the number of degree 1 representation of G. Now, we already know that since G modulo bracket Gg is abelian, so that implies that the hat of this the quotient. So, this is going to be isomorphic to G modulo bracket Gg, and if you think about it, this is the dual group. The dual group actually captures all possible finite dimensional irreducible representation of this abelian group. So, that means this is going to count exactly the number of finite dimensional irreducible representation of G modulo bracket Gg. So, that tells us that this number is exactly same as the cardinality of G modulo bracket Gg. So, now Lagrange's theorem tells us that the cardinality of G is exactly cardinality of G divided by cardinality of Gg times the cardinality of Gg. So, that proves that this number actually divides the cardinality of G. So, these are some important facts. So, later we will use this lemma or this proportion in order to actually compute character table of some smaller groups. So, this is actually very important observation. So, now let us actually use this to prove this group theory result that I actually promised. So, if you take actually group which has order PQ, where both P and Q are prime numbers satisfying the following condition, P less than Q and Q not congruent to 1 modulo P, then we can prove that this G is abelian using representation theory. So, let me make the statement. So, let us call it as corollary. So, let PQ be prime numbers. So, we assume that so P is less than Q and Q is not congruent to modulo P. So, with this assumption, so we can actually prove that then any group of order PQ, So, that must be abelian. Again we use the characterization of abelian groups in terms of irreducible representations. So, here is the proof. As before, again we call d 1 etcetera d s to be degrees of non-isomorphic irreducible representations, d 1 etcetera d s. These are the degrees of irreducible representations of G. So, we can assume that without loss of generality d 1 is 1 corresponding to one dimensional trivial representation. So, now we can actually see that each d I divides p q. So, each d I divides p q. So, that would imply that either d I is 1 p or q or p q. So, now since we have this equation which actually relates cardinality of G and sum of d I square. So, from this you can see that so d I cannot be p q for all I greater than 1. Already d 1 is 1, because of that you can see that d I cannot be p q. So, now that would imply that d I is either p or q. So, let us see d I cannot be q. Suppose d I is q. So, then that would imply that the cardinality of G is p q. So, p q is greater than or equal to 1 plus q square, which is greater than or equal to q square. So, that would imply that p is strictly greater than q, which is a contradiction because we assumed that p is strictly less than q. So, we cannot actually have d I equal to q. So, we can only have either d I is 1 or p. So, now what we are going to do? We are going to just denote the number of I such that d I equal to 1 to be m. So, let us call m to be the number of I, of course, from 1 to s such that d I is 1, and call k to be number of I such that d I to be p. So, now from this we can easily see that the cardinality of G, which is p q, which is exactly equal to the number of d i's which are 1, which will be m, plus so the number of d I which are p, that is exactly k. So, k times p square. So, we get this equation from this equation. So, now we have this equation p q equal to m plus k p square. So, let us actually try to understand that. So, p q equal to m plus k p square. So, now if we go back, so we have we claim actually p also divides m, or we can simply say that p is at least, so at most m. So, m is at least p. So, why is that true? So, for this we just use the previous lemma. So, we know that the group actually the number of degree 1 representations. So, that is exactly going to be the cardinality of G divided by the cardinality of the commutator. So, this m is supposed to be the cardinality of G divided by the cardinality of the commutator. So, which actually divides p q. So, this m divides p q. So, now since m is actually at least 1 and divides p q. So, the chances are, so m is supposed to be either 1 or p or q or p q. So, now if we actually look at the possibilities, so we can also argue like this. So, since order of G is p q, so we have actually using Cauchy's theorem, there are elements of order p and elements of order q. So, there is an element of order P and element of order Q. Okay, so this requires actually some information about the commutator. So, let us go back. Okay, so using basic group theory, maybe I will leave it as exercise, that the cardinality of G modulo bracket GG when the cardinality of G is PQ. So, that is going to be at least P. So, use basic group theory to prove this. So, then that would imply that the number of degree 1 representations of G, which is exactly equal to the cardinality of G divided by cardinality of GG. So, that is going to be at least P. So, now if we go back, so we have PQ, which is exactly m plus k p square, and this m is at least P. So, indeed we want something stronger. So, we want to actually have P indeed divides the cardinality of G divided by the cardinality of GG. So, this is also something you can prove using some basic group theory. So, in that case, so what happens here? So, we have PQ equal to m plus Kp square and then P divides m. So, from this we conclude that this Q is going to be m by P plus Kp. Now, since m actually divides this PQ, so since m divides PQ, that would imply that m is either Q or PQ. So, now we can see that m cannot be actually, so sorry, m also can be P or Q or PQ. So, our claim is going to be m must be P. So, m cannot be actually anything other than PQ, m must be PQ. So, that would actually tell us that the number of degree 1 representations is exactly the cardinality of the group. So, why this is true? So, let us see all possibilities. So, since m divides PQ and P divides m, so these are all the things that we have already observed. So, P divides m and m divides PQ. So, that would imply that m is either P or PQ, because P actually divides m. So, this possibility is not there. So, that means either it is P or PQ. So, it is enough to prove m cannot be P. So, let us say m is P. So, then using this equation you can see that this Q is exactly 1 plus Kp. So, this would imply Q equal to 1 plus Kp, that would imply that Q is congruent to 1 modulo P, which is a contradiction. So, this actually tells us that we can only have m equal to PQ. So, that is exactly the number of degree 1 representations of G. So, that means G must be abelian. So, this proof indeed uses the fact that whenever you have a group of order PQ, so then P indeed divides the quotient of cardinality of G divided by the cardinality of the commutator subgroup GG. Okay, this is something I am just going to leave it to you. I guess this can be proved using Cauchy's theorem. Okay, so this actually kind of gives some another way to prove this kind of deeper result using representation theory. So, what we are going to do ultimately we want to prove Burnside's theorem, which actually tells something about the group which has order p power a q power b, both p and q are prime. So, Burnside's theorem asserts that this group of order p power a and times q power b, that must be solvable. So, I do not want to actually get into the definition of solvability and so on. So, I am going to prove a equivalent version of Burnside's theorem. So, that is going to be the ultimate application of representation theory in group theory. So, which we can actually see later. Okay, I will stop here, then we will continue with computing some character tables in the next class. Thank you.